Thank you. Okay, so the bearing capacity of pile. So a pile, it's a deep foundation, and these foundations, they are used to transfer the loads towards layers that can support the forces transmitted by the superstructure. And we have mainly for piles some criteria to define. It's not very accurate, but a pile is slender, so the slenderness ratio is over 6 about. And there are in the deep foundations, it's quite larger. We have piles, but also micro piles that are piles with a small diameter, but also the barrettes, which are structural foundation elements more larger than pile, but they are calculated almost in the same way. So to transmit the load applied to the pile to the soil, in fact, there are two elements. So one element of resistance comes from the tip, the end bearing, so the RB resistance. This is the notation from the Eurocodes, and RS, which is the skin friction resistance, the resistance due to lateral contact of the pile with the soil. So those two elements have to be evaluated for calculating the pile bearing capacity. One particular case is when the skin friction is much higher than the end bearing resistance. We say that it's a friction pile. So just vocabulary, but not so important. There are a large number of pile techniques. So just for French standards, we have 20 categories of piles defined in the standards. The main materials used in the history are wood. The first example comes from more than 4,000 years in the past, steel since about 2 centuries, and concrete in the 20th century. So wood is becoming in the fashion now again, but for other reasons. There are two main types of installation. This is quite important because it depends on with the type of installation, we will modify plus or minus the contact of the pile with the soil. So soil excavation, so typically a bored pile, or soil displacement, so typically jacked or driven piles. So the difference we can see maybe here, I don't know if it is very clear. This is an experiment coming from Switzerland, from Lausanne. And in this case, you can see on the left, a pile that has been bored. So this is an artificial soil mass made of layers. So you can see the horizontal interface time to time. And so with the bored pile, there is almost no modification of the interface that are really always horizontal. And for a jacked pile, it's very different because you can see the pile, so the soil has not been removed and the pile has been installed with the force. And so there is high deformation here in the contact of the pile. So those pictures have been taken after installation and after removing half the pile and half of the soil in order to see the cut. So it is also possible to simulate numerically those differences in the installation, as it has been done here on this example. Okay, so we can split the applications in two parts. So if we have a compressive load, we will use the both end bearing resistance and skin friction. But if we have a tension load only the skin friction will be taken into account in the resistance of the pile. Okay, so we have different techniques to identify both those both resistant forces. So full-scale testing loading test. This is allowed by the Eurocodes. In situ soil test. So this is called the model pile method. Laboratory soil test. So this is called ground model method, or dynamic impact test, which is a specific test developed for piles. So for instance, the classical soil investigation is a cone penetration test. So it's a small cone with instrumentation, with a force sensor close to the tip. And with this cone, we can record some soil parameters like the resistance of the soil, the cone resistance of the soil, which is used for calculating the resistance of the pile following different methodologies. Okay, so I spoke about vertical loading, but we may have also horizontal load. So it's the case, for instance, if we design a bridge funded with which piers are founded on piles, we may have accidental or exceptional horizontal loading due, for instance, breaking of a train that pass on the bridge. And so we have to take it into account and to design correctly the piles. Of course, for offshore wind turbines, the horizontal pile is also a very important point, because the horizontal load may reach a very high value in comparison with the vertical load, which is not the case of buildings where the horizontal load are only due to wind effect, for instance. Okay, so we can use different methods to identify the lateral load. So based on in situ soil test or laboratory soil test. And the methodology, classically, for flexible piles or long piles, it's to simulate the soil reaction at different level by spring or non-linear spring, or a set of springs that react. So this is called a reaction curve. So P is the reaction of the soil, and Y is the displacement of the soil. So depending on the depth and the characteristics of the soil, we have different PY curves, and we have to use this data in order to calculate the total behavior of the pile. So I move to physical modeling at different scales. So for instance, here there is pictures of suction caissons. So you can see on the left the full scale. So it's something of 5, 6 meters in diameter, 30 meters in long. And at the scale here on the centrifuge on the right, scale 1/75. So it's quite smaller. And we can test this type of foundation. So we have seen this morning the importance of reproducing the soil properties, and it is possible if we perform a small scale, not at 1G but at NG, where the soil properties, for instance, the Gmax, is correctly scaled on the small scale model. Concerning small scale in a centrifuge, if we reduce the scale of a pile, we have to take into account what are the main parameters. So for instance, for a vertical load, the external surface has to be scaled, because it's an important parameter, and depending if the pile is open or closed, we have to take into account this phenomena. But we cannot reduce the thickness of the pile as much as we want, because we need to be able to build the pile by itself. So sometimes this parameter is not totally scaled, so we have to take care about that. And we may have also some scale effect at the contact between the base of the pile and the number of grains in contact with this structure. So we know how to avoid scale effect. For instance, in clay, there is no scale effect. In sand, we have to respect some rules that have been established by the scientific community. Concerning the pile behavior under lateral load, here the main parameter is the flexural rigidity, so the product of E and I. E, the Young modulus, and I, what's the word? Sorry? The second moment, okay. But to be accurate, the inertia, in fact. And in this case, as I mentioned previously, to have the good flexural rigidity, for instance, it could be a good idea in the centrifuge at small scale, either in order to be able to make this small scale pile with a possible thickness, we change the material. So instead of steel, we use aluminum. And for that, we can increase a little bit the thickness, and so the inertia, the E as the I, sorry, as the E, the Young modulus, is a little bit reduced in comparison. So it's important before starting experiment to know how it works and what are the main parameters that we have to fix in order to perform experiments that we can compare with other approaches, design rules, or numerical approach, or in-field test, and others. Okay, so I move a little bit rapidly on this example. So here it's a real example on which we have worked in Nantes about 20 years ago, more than 20 years ago. It's the bridge, the Karilaos Trikoupis bridge, so the Rion-Antirion bridge, close to Patras. And this bridge is in a seismic area. And the idea of the designers was to improve the soil, the soft soil, by installing rigid inclusions that are tubes of 2 meters in diameter and 25 or to 30 meters long, and to place over this reinforced soil a mattress of granular material in order to be able to allow displacement at the base of the pier and also rotation. So the granular layer is the weak zone where the strains will be concentrated in case of earthquake. So this bridge was something the biggest at this period. I don't remember what, if it's the span or the length, or I don't remember exactly. But nevertheless, in the centrifuge, the foundation looks like that. So we scaled by 100 the size, and we apply also factor 1/3 because our container are 90 centimeter in diameter, so we could not test a 90 meter at 100 G, so we reduced a little bit. And those tests were compared with numerical analysis performed by the GDS company in Paris, who designed the foundations. Another example that have been done and developed more by University of Dartmouth. It is a monopile, so tested in different conditions. And you can see here on the curve the effect of the diameter of the monopile tested on horizontal load on the wall behavior. So we can see that the maximum force is, of course, higher for greater diameter. Other example here at full scale. So these are very nice experiments performed in UK. And you can see that at full scale, the diameter is very large with very big jacks in order to apply the loads in this case. And it is possible to make lateral horizontal load, but we need reaction support for loading the piles laterally. Okay, so we have seen this morning this afternoon a nice centrifuge here. There is an older one on the west coast and north. And as it has been mentioned by Professor Yanis this morning, one of the great advantages of a small-scale model in centrifuge is that the forces needed to be applied on the structures are reduced by the factor of 1/n squared. And so instead of having big jacks to apply the load, we need only small ones. And that's a great advantage that makes very popular this technique because it is quite easy once you have produced the G level required for the simulation. Okay, so here I have an example of impact driver that we have developed in Nantes, and I think I have a small video, yes, here. So it is a system where you can see a mass is running, is turning, and it is guided by a wave shape system in green. And when it falls down, there is a shock, and then the pile is driven vertically. I have also this example. This is an example of the installation by driving. So we start the centrifuge. So you can see the cables that are submitted to a higher and higher G level until 100. And then the driving starts. So the image has been accelerated by 60. And when the depth of embedment required for the experiment, so we will stop the driving, and the driver, which is guided by a hydraulic jack, will be removed vertically. And then in this case, we wanted to study lateral behavior of monopiles. And so there is a second jack, an electric jack, which is located, which is moving horizontally, located to apply the load exactly on the road, horizontal road that you can see in red, to study the behavior of the pile. So we perform monotonic and also cyclic loading in this case. If we forgot centrifuge and we come back to 1G test, so we have to take care about the scale factor. So they are not exactly the same, of course, because the G level has not been changed. And so we have to take care about here, for instance, the scale factor is the ratio between the prototype and the model. So there is certain value. So for instance, for displacement, we will have the power 1, and for force, it will be power 3, and moment of inertia, here it would be power 5. So we have to know that in order to perform the test and to interpret correctly the test performed. And the scaling, so it's written in red, it's very important. The scaling has to comply with the goal of the experiments. So always, it's the case in plenty of example in your life. You have to comply with the goal of what you are doing. So you use the good tools, have the good behavior, and for doing what you want to study. Here it's also some pictures you can see about field scale tests. So those tests are very impressive because very large. It's necessary to use a reaction pile. and very big jacks are used in order to apply the load. So here those tests have been done for studying cyclic loading, but well, for dynamic loading, it's another, it's more complex. Here in this, I will not detail so much, but in this table, we tried to put colors for the different approaches, small scale, medium to large scale, and field scale for different cases. So for instance, in the first line, comparability of soil model in situ conditions. So field tests are, of course, more adapted than the others, but they are not so bad, and so on. And so you can see, well, so we have different examples. So it's just a guide for thinking about those things. And so you can see for different, for instance, for cost, the last line, while in centrifuge, if you have the centrifuge, the cost is not so important, but in field, of course, you need a lot of material to perform the test. So if you want to perform test, you have to choose the scale. So we have a methodology here. I will not detail so much. We will discuss later. But this is a chart just to think about the different steps that we have to follow. Particularly here in centrifuge. So we, of course, we do not choose the scale in the first step because there are plenty of different considerations. And for instance, the instrumentation available. So for instance, if we want to measure a force and we have sensors of, I don't know, diameter of 1 centimeter, and the pile we wanted to design was 0.9, maybe we will change a little bit this scale to have to adapt exactly the diameter to the instrumentation. So concerning data collection from instrumentation and measurements, of course, it's very important. If we perform tests, we record data, and so so there are different sets of parameters that can be measured quite easily. So the force, so generally the force sensor, they are based on gauge sensors, on strain measurements that are calibrated in order to deliver force sensing. We have the displacement. If we measure displacement and force, we can calculate the work. So this is quite important. So there are plenty of different techniques used. The trend also is to use non-contact, like laser sensor, more and more, because they are cheaper than they were in the past. And also they disturb less the phenomenon, especially if the force is reduced. So the laser apply no force on the structure. So with instrumentation on the model, we have used strain gauge. Outside the pile, for instance, inside the pile, also for closed-ended piles. And for recently, we used fiber optics that are quite accurate also and waterproof and can be integrated in the thickness of the pile. Concerning data loading, we have to take to ask this question. It's obvious, but of course we have to wonder what could be the frequency. Do I measure each second, each minute, each year the parameter, and how I store the data? So those points. Well, in each lab, you have the answer before asking the question. We have equipment for that, but depending on the phenomena, we have to adapt the good frequency. There are special cases, and for instance, in centrifuge, we have different systems for data acquisition. In some cases, the data acquisition is close to the axis of the centrifuges. The centrifuge, sometimes it's in the basket. It depends really on what we measure, and what if the signal can be conducted far away without perturbations. So, for instance, for a dynamic record in our centrifuge, we have a memory which is in the basket, and then we read the memory and collect the data in the control room time to time when after the test. Another thing that you have to have in mind is that usually we measure voltage or intensity or frequency in some cases, and we have to transfer those roof measurement so that in force, in Newton, in millimeters, and so on, and that requires calibrations. Okay, so I spoke about the frequency of the record. It's important. And afterward, when you have recorded the data, you have to analyze that. So for that, it's necessary to know, well, where is the truth in between what we have expected and what we have measured. So for that, there are plenty of softwares. So maybe you are familiar with one of them. More or less powerful depending on what you record and what you want to exploit. Also concerning the measurement, they can be more or less accurate. And for instance, in this case, we have the real temperature measured and some points of measurements. And so if we make the difference, we have some scattering in between the truth and the measurement. So we have to take it into account and to integrate possibly in a statistical approach. Okay, I move. Another problem that we can face is the case where we have strange measurements. For instance, we measure a temperature of about 3, 4, 5 degrees, and then we have about 20 degrees. So you have to, we don't know why, maybe it's an electrical problem. So you have to be critical about, is it possible? Is there a mistake? And another point that we have to face is sometimes it comes back to 0. So we measure something and we have a cut in the chain of instrumentation, and there is a 0. So we have to clean those data for interpretation. And in the analysis, you will see later on the example with Professor Zackert, but we have also the opportunity to make comparison with numerical analysis on the behavior, for instance, here, behavior of pile under lateral loading. Okay, so, well, I finished the introduction. So, well, I don't know if you are very familiar with measurements or is it new for you?